Welcome all. Welcome to today's online class. Today we discuss the second part of General Introduction to Spectroscopy or Molecular Spectroscopy. In the previous class we learned that the total energy of a molecule in gaseous state is equal to the sum of various energy components according to Born-Oppenheimer approximation that include rotation energy, vibration energy, electronic energy as well as translational energy. But being not quantized, translational energy is neglected and the equation reduces to total energy is equal to rotation energy plus vibration energy plus electronic energy. According to Born-Oppenheimer approximation, that is from quantum mechanics, it is also that all these energies are independent of each other. So when there is a change in energy, we can now write delta E total, that is the total energy change of a molecule will be equal to delta E rotational plus delta E vibrational plus delta E electronic. We have already learned the origin of these different types of energy. That is how a molecule is getting rotation energy, because the molecule can rotate about an axis passing through the center of gravity. Like for example, if it is CO2, we have seen in the previous class, carbon, oxygen, it's a linear molecule. If you take this axis, that is axis passing through the center of gravity, the molecule can rotate like this. Okay, it can rotate like this, and that gives rise to rotational and kinetic energy. And origin of vibration energy is that the bones can undergo vibrations like stretching, elongation and contraction like this, and it can also undergo bending vibration like change in bond angle. Whereas stretching is change in bond length, bending is change in bond angle. Like this, there can be vibrations taking place in the molecule which give rise to vibrational kinetic energy. And finally, electronic energy is by virtue of the electrons present in the molecule in various electronic energy levels. Now, these three energies, if we compare, the magnitude is that electronic energy is having the greatest magnitude, or it is maximum quantized, decreases to vibration energy and further decreases to rotational energy. So keep this in mind. That means in a molecule, the most spaced energy levels are electronic energy levels. Okay, that is having maximum separation. Then comes vibrational energy, then comes rotational energy. So we can represent all these energies in one single energy level diagram. Here you can see this is the energy level diagram. Okay, let us see what are the various energy levels here. This red line represents the electronic energy, the ground electronic energy level, and this is the first excited electronic energy level, there will be third, etc. So this is the energy gap, electronic energy gap of electronic energy levels. Okay, this much. Now each electronic energy level is further divided into various sub-levels. What are these? The black lines that represents the vibrational levels. Okay, so each electronic level is further divided into vibrational levels. A point to be noted here is the ground vibration level is a little above, means there is an energy gap here. This is called 0 point energy, minimum energy possessed by all the molecules. Even at 0 Kelvin, you cannot stop the vibrations. That is the point. There will be a minimum inevitable amount of energy, vibration energy associated with every molecule. Okay, so this is the ground vibration level. So this much is the energy. See, we use certain quantum numbers for energies, like you use for quantum numbers for atomic orbitals. Here these are the quantum numbers for the vibrational energy levels. I have told you that spectroscopy, or remember that spectroscopy is actually a quantum mechanical problem. Each spectroscopy like vibrational spectroscopy, rotational spectroscopy, etc. are considered as a quantum mechanical problem. We will have a model, a quantum mechanical model, and we will write Schrodinger equation, incorporate various energy parameters and solve it, and the solutions will give you some quantum numbers which restrict the energies. You have certain allowed energy levels, right? So in vibrational energy levels, we use this symbol nu as the vibrational quantum number. Nu equals 0, 1, 2, etc. This is the vibrational levels in the ground electronic state. Okay, these are the vibration levels in the first excited electronic state, and here this is the ground vibration level, nu equals 0. This is the first excited vibration level, second, etc. Finally, rotation energy levels are coming still smaller. Each vibration level is further divided into rotation levels. The blue lines you can see, right? These are the rotational levels which comes within a vibration level. Okay, the energy gap is still smaller, for which we use the quantum number. Rotational quantum number is J. J equals 0, 1, 2, 3, etc. Okay, this is the ground rotation level, first, second, etc. Actually, this is to be shown like this. J equals 0 is, it is here only. J equal 0 is the first black line only, then 1, 2, 3, it goes like this. Okay, 0, 1, 2, 3, like this. Here also that correction will be the 0, 1, 2, 3. The point is that in rotational energy there is no 0 point energy. You can stop the rotation of a molecule totally. Okay, you can arrest it by going into condensed states like liquid and solid, and you can have no rotational energy associated with the molecule, but you cannot stop vibration. Even at 0 Kelvin, it is that there is vibrations taking place. So that molecule is having a minimum vibration energy all the time. Fine. Now coming to the different types of spectroscopy which we can understand from this diagram is, the first one, see, if due to rotation, molecule will have various rotation energy levels, right? And molecule will be preferably in the ground rotational level. Okay, if we are giving a radiation of suitable frequency, molecule can go to the higher vibration level, right? Molecule can go to a higher vibration level like this, amounting this much energy. So by absorbing this much energy, it can go to this vibration level, or by absorbing a little more energy, it can go to the next excited vibration level. So these are called vibrational transitions. It is like, suppose a molecule is rotating with a very lower frequency, or like an angular velocity, suppose. If you are giving radiation, it can rotate little faster, like your ceiling fan. If you regulate it, if you change the regulator, its rotation will become quicker, like that. So it is absorbing energy and going to a higher rotational frequency, right? That is what is happening during a rotational transition. When we say that molecule goes from lower rotation level to higher rotation level, it means physically that the rotation becomes faster. In the process, it absorbs energy. Now, which radiation is suitable for this transition? That is based on the magnitude of energy. See, rotational energy is coming in the order of 0.01 to 1 kilojoule per mole. That is the energy, magnitude of energy of this rotational levels roughly. This is the energy. This energy is given by a particular radiation. Which one you know? That is microwave radiation give rise to this transition. So rotational spectroscopy is obtained by using microwave radiation, because that is coming from Planck's equation, E is equal to hc by lambda. Okay, so when energy changes, wavelength will change. So for getting this energy, for rotational transition to occur, we need a radiation having a corresponding wavelength, and that corresponds to microwave. So remember, rotational spectroscopy is also called microwave spectroscopy. Actually, this is what is happening in our microwave oven in the kitchen. You can make cooking very fast. You can heat a dish very quickly in a microwave oven. What is happening? Inside the oven there is microwave radiation generated, produced, and water molecule present in any foodstuff. In any foodstuff there will be plenty of water molecules all over the stuff, and these water molecules absorb microwave radiation and undergo rotation faster. So all the molecules are rotating, and that will heat it up, and it causes heating and cooking. Okay, that's the principle of microwave oven. Right now, so rotational spectroscopy is otherwise called microwave spectroscopy. There are synonyms for each spectroscopy. One is based on the type of energy transition taking place. Here it is rotation energy transition. And the second name is based on the radiation used for the purpose, that is microwave radiation. So rotational spectroscopy or microwave spectroscopy. So that is the first type of spectroscopy we come across here, rotational spectroscopy or microwave spectroscopy. Right? Now secondly, suppose a molecule is undergoing vibrational transition. See, it is now here. Suppose from nu0 to nu1 it is going, or nu0 to nu2 is going. You can see that this requires larger energy. The energy value is nearly 1 to 100 kilojoules per mole. That is energy gap corresponding to vibrational energies. This much, so energy is larger, right? So when energy is larger, wavelength is smaller. So we need a radiation which is smaller in wavelength. It is interesting that for vibrational transitions, we are using which radiation, The next one, that is IR radiation. So IR is used for this transition. So we can say this is vibrational spectroscopy, also called IR spectroscopy. So the second spectroscopy is vibrational or infrared spectroscopy. Okay, why it is called so? Because here there is vibrational transition taking place in the molecules. It is that suppose the bond is vibrating like this, like a spring at a particular frequency. When you give energy, IR radiation, it can absorb and go to a higher frequency like this. Okay, that is what is meant by the transition. So vibrational spectroscopy, also called IR spectroscopy. Now finally, coming to the next one, electronic energy gap is the maximum, and it is ranging from 10 raised to 2 to 10 raised to 4 or 10 raised to 3 to 10 raised to 4 kilojoule per mole, like some 1000 or even 100 to 10,000 kilojoule per mole. Very large energy gap, which require still smaller wavelength. Smaller the wavelength, greater the energy. We go to the next region, that is visible and UV. These two are used for electronic transition. So electronic spectroscopy is also called UV visible spectroscopy. So that's the third one, electronic or UV visible spectroscopy. So three types of spectroscopy which we come across from this diagram. Among this, we have to go into the details of these two types of spectroscopy, vibrational and electronic. Remember, in all these spectroscopy, between the that during spectroscopy we send an electromagnetic radiation to the sample or the molecule, and there occur an interaction and absorption takes place, during which molecule undergo transition from lower energy to higher energy, which is governed by selection rules. Okay, I will talk about selection rule later. Now, in all these three types of spectroscopy, the interaction is electrical. That means when there is these kinds of rotation, vibration or electronic transition, it is the electrical component of the radiation which interact with the electrical dipoles of the molecule. When we go to the details, we'll understand that. So, in this type of spectroscopy, electrical interaction takes place between the electromagnetic radiation as well as the molecule. So that transition takes place, absorption takes place, giving the spectrum. Whereas we have another type of spectroscopy to discuss in our syllabus is a very special type, that is Nmr Spectroscopy, which is different. As the name indicates, nuclear magnetic resonance. It's a magnetic type of interaction between the radiation and the nucleus. Here it is related to the nucleus, magnetic property of nucleus. And for this NMR, the radiation used is radio waves, because the energy gap for this magnetic level is corresponding to the energy of radio waves. All these we will deal in detail in the coming classes. Okay, so this diagram is very important to give you a good impression about what is spectroscopy and what are the types and why we use different types of radiation for different types of spectroscopic technique. Okay, now regarding selection rule, what is meant by selection rule? See, in the diagram we have seen that, for example, in vibrational levels, there are different levels like nu equals 0, 1, 2, 3, etc. Okay. Normally, let us consider for example, vibrational spectroscopy. Molecule will be normally in the ground electronic level, ground vibrational level, right? Now the question is, from this ground level to which excited vibration level the molecule can go, whether to 1 or to 2 or to 3, like that. There's a question. Selection rule give answer to this. Selection rule indicate the change in quantum number which is allowed for a transition. Okay. In vibration spectroscopy, it is that delta nu, the change in quantum number, can be plus or minus 1 normally. This is a normal case. What is plus or minus 1 means? If the molecule is in 0 state, it can go to 1 only, not to 2. These are not possible. Okay. Suppose the molecule is in 1, normally it will be in ground state. Sometimes the molecule may remain in an excited level from where it can go to 2 only. That is this selection rule. Plus 1 indicates absorption. What does minus 1 indicate? If a molecule is in 1, if it is coming down, it can come to 0, like that, from 2 to 1. So, this is selection rule. Plus indicate absorption. Generally, we are concerned with absorption spectra in our discussion. Minus indicate emission. We are generally not discussing emission here. Okay, so selection rule is the one which restrict the transition. It indicate, you may note that selection rule indicate change in quantum number which is possible during a transition. Change in quantum number during a transition. What is the importance of the selection rule? It restricts the transitions. It restricts the number of transitions. See, number of transitions are limited. So what? So the spectra will be simple. The spectrum given by the molecule will be simple. Suppose there is no selection rule, what would happen? All transitions are possible. Molecule can go from any level to any level. So what? So correspondingly different amounts of energy will be absorbed. All of them will give peaks. So many peaks in the spectrum, which is of little use. Right? It's very difficult to interpret such a spectrum. So selection rule restrict the number of transitions and it simplifies the spectrum. Even though there is in the rotational spectroscopy also, delta J, it is equal to plus or minus 1. That is the selection rule again. The change in rotational quantum number can be 1 only. That is, from J equals 0, molecule can go to J equal 1 only. Okay. However, in molecules, there occur transitions which are against selection rule. So there are two types of transitions: allowed transitions and forbidden transition. What is that? Allowed transitions are transitions which are in agreement with the selection rule. Transitions which follow selection rule. That is called allowed transitions. Forbidden transitions are transitions which violate selection rule, which are not following selection rule. This also occurs sometimes due to certain relaxation techniques or certain approximations are there. So both are there. You can easily distinguish the two. How? Allowed transitions will be very intense. The peak will be very intense because it is most likely, most probable transition. So allowed transitions are very intense peaks, and forbidden transitions will be very weak signals you get. You can distinguish them that way. Okay. Finally, how we record the spectrum. In different spectroscopic techniques, the output or the spectrum is plotted in different way. For example, in UV visible or electronic spectroscopy, the plot is generally like this. Okay, the spectrum is plotted like this. It is plotted between absorbance or sometimes intensity versus lambda for convenience. And then you get peaks like this. This is how you get the electronic spectrum. Like a hump you get, a broad peak you get. Okay. This is the case of UV visible spectrum. In the case of IR, the plot is different, the variables are different for convenience. It is not absorbance, it is the transmittance or percentage transmittance is plotted against not wavelength. The more convenient is taking wave number. That depends on different techniques. Here wave number is used for plotting, and here it is transmittance is plotted. So this is absorbance. So transmittance will be just opposite. So the peaks comes down like this. This is how you get the IR peaks down. Transmittance is plotted. So this is how spectra is plotted. So these are the basic ideas of spectroscopy. In the coming classes, we discuss in detail about vibrational or infrared spectroscopy. After that, electronic or UV visible spectroscopy.